Hello class. In this very short PowerPoint, we're going to look at decision tree analysis. I've included this in the course with the technology applications because I want you to see how Excel can be utilized to help you really efficiently solve capacity problems, which you would do by hand using a decision tree, which could end up being laborious and time-consuming, and Excel can do it quite efficiently, and it looks really pretty in the nice and neat decision tree. However, before we look at the technology, I think it's so good to have our understanding grounded first in what we're doing by hand. It gives us a stronger conceptual understanding and greater procedural fluency with the topic at hand. So we're going to look at an example and set up a decision tree by hand, and then I'm going to show you the same exact one set up in Excel. Now, you do have to download a specific add-in, and Excel is going through some changes with their decision tree add-in, so we're going to use a specific one that I'm just going to have you download a free trial for. I like this one because it offers several tutorials to help you design your decision tree, so that's why we're going to use it. I'll give you all the directions for that, but for now, just go ahead and proceed through the PowerPoint, follow along with the example, make sure that all the branches and the nodes and the final expected value and the concluded decision make sense, and if you have any questions, don't hesitate to shoot me an email.
The next topic that we're going to look at is using decision trees to evaluate capacity alternatives. A convenient way to lay out the steps of a capacity problem is through the use of decision trees. A decision tree is a schematic model of the sequence of steps in a problem and the conditions and consequences of each step. Decision trees are composed of decision nodes to and from them. Usually square nodes represent decision points and circular nodes represent chance events. Branches from decision points show the choices available to the decision maker. Branches from the chance events show the probabilities for their occurrence. In solving decision tree problems, we work from the end of the tree backward to the start of the tree. As we work back, we calculate the expected values at each step. Once the calculations are made, we prune the tree by eliminating from each decision point all branches except the one with the highest payoff. This process continues to the first decision point, and the decision problem is thereby solved.
I mentioned that decision trees are great for analyzing capacity problems, so that's what we're going to do, and we're going to look at an example specific to this. I have the example on the screen, and I'll just go ahead and read it aloud. It says that the owner of Hacker's Computer Store is considering what to do with his business over the next 5 years. Sales growth over the past couple of years has been good, but sales could grow substantially if a major proposed electronics firm is built in the area. Hacker's owner sees 3 options. The first is to enlarge his current store, the second is to locate to a new site, and the third is to simply wait and do nothing. The decision to expand or move would take little time, and therefore the store would not lose revenue. If nothing were done the first year and strong growth occurred, then the decision to expand would be reconsidered. Waiting longer than 1 year would allow competition to move in and would make expansion no longer feasible. Okay, so we need some meat and some numbers to this problem. So let's assume that you are given the following conditions and assumptions. Number 1, strong growth as a result of the increased population of computer fanatics from the new electronics firm has a 55% probability. Number 2, strong growth with a new site would give annual returns of $195,000 per year, whereas weak growth with a new site would mean annual returns of $115,000. Number 3, strong growth with an expansion would give annual returns of $190,000 per year. Weak growth with an expansion would mean annual returns of $100,000. Number 4, at the existing store with no changes, there would be returns of $170,000 per year if there's a strong growth and $105,000 per year if growth is weak. Number 5, expansion at the current site would cost $87,000. Number 6, the move to the new site would cost $210,000. Number 7, if growth is strong and the existing site is enlarged during the second year, the cost would still be $87,000. Number 3, operating costs for all the options are equal.
In the slide following this one, we're going to construct a decision tree to advise Hacker's owner on the best action. In this decision tree, you'll notice that there are 2 decision points which are shown with square nodes and 3 chance occurrences shown with round nodes. In this slide, in the table, the values of each alternative outcome shown on the right of that tree diagram are calculated in the table on this slide. So as you're looking at those values, you can refer back to this table if you would like to see how they were calculated. Looking at the rightmost values in this table, you'll see that if we do nothing now and then expand in year 2 due to strong growth, we make less than if we do nothing for all 5 years. So we can totally eliminate that choice, and I've indicated that in the table on this slide.
Okay, so this diagram shows our tree. We've constructed it based on the numbers that we got from the previous slide. Notice that we have 2 decision nodes on this tree, which are indicated with square nodes, and we have 3 chance nodes, which are indicated with circles. I've also put in our probability. Strong growth is 55%, meaning weak growth would be 45%, and those repeat at each of those branches from move, expand, or do nothing. Notice that those final values that we get at the end of all the branches are found by taking our revenue and subtracting the moving cost from them. So we have those in our previous table, but if you weren't sure where those were coming from, that's how we generated them. So if you remember from slide 5, we said that we would eliminate branch 5, which says expand in year 2, because it's the least profitable thing to do. After we've done that, we can calculate the expected values associated with our current decision alternatives. And we do this by simply multiplying the value of the alternative by its probability, and then we sum the values for strong and weak growth associated for that particular branch to achieve the expected value of that given occurrence. So to calculate the expected value of moving, we would multiply 0.55 times 765,000 plus 0.45 times 365,000, and we achieve a monetary value of 585,000. The expected value of expanding is found by multiplying 0.55 times 863,000 plus 0.45 times 413,000, and that gives us a total value of 660,500. The expected value of doing nothing is found by multiplying 0.55 times 850,000 plus 0.45 times 525,000, and that gives us a final value of 703,750. So our analysis would indicate that the best decision, the most monetarily worth it, the most lucrative, would be to do nothing. Here's the cool thing. Since you're going to be constructing your decision tree in Excel, once you complete the table that you do in, as we did in slide 5, you just plug the numbers in, and Excel calculates all of the expected values and tells you which branch is going to be the one that generates the optimal solution for you. So I think you're going to like it because it's going to cut down on some of the calculating.